So this is the video where I'm putting it all together. I've been doing this for a good 30 minutes already because I understand this is a lot to look at right now, a whole lot. Just as a quick summary again, we are discussing atomic radius, ionization energy, and electronegativity. Atomic radius is the size of the atom, and I believe the most important thing when looking at all three of these trends. Ionization energy is the ability to protect your electrons, and electronegativity is the ability to attack others' electrons. Again, we've been discussing things using the words with the graphs. I'm going to take all this away. Because I'm going to lock this really quickly. You're not going to really have a lot of this information when you're looking at the periodic table. You're not doing this. You need to know that positive charges are going to be all in the orange, which we saw from another video. You're going to need to know that the negative stuff for the brown area are going to be trying to lose electrons. What you can really simply see is I have magnesium somewhere over here, and I'm going to have you compare these guys. Well, which one has the biggest radius? Which one has the most ionization energy? Which one has the electronegativity? So let's just jump right in, okay? This might take multiple videos to explain, but I think we can do it. So in terms of atomic radius, big to small. Looking at this, I know and I can tell that, well, francium is the biggest element. It helps knowing that. So the closer you are to francium, the bigger you are. So we know, because of the number of shells, strontium has 5 shells, being in the 5th row, and antimony here. And this is what I refer to as the box. Well, strontium has less protons than antimony. I'm looking 38 versus 51. So I know that strontium is going to have less attraction on it. So strontium is going to be the biggest. Antimony is the second biggest. I know that just because, again, strontium is closer to francium. That's the pattern. Again, 5 shells beats 3. And that pattern works again. Magnesium here is got 12. Again, both of these have 3 shells. Magnesium, phosphorus are both in row 3. Well, 12 protons isn't going to pull as well as 15. 15 wins. So the 15 is going to be brought closer in and be smallest, which means, kind of a cool way, ionization energy and negativity, big to small, it's the opposite. Just like we talked about before, right? Phosphorus, magnesium, antimony, strontium. And why is that? Well, one, phosphorus is trying to gain 3 electrons, just like antimony. So these guys are trying to gain electrons, not lose. So they're going to have very high ionization energies. But the problem is these two are smaller. Phosphorus has 3 shells. Magnesium has 3 shells. So this is the smallest and is going to have the most fight. Then magnesium, then antimony, then strontium. Again, small atoms want to protect and want to defend. Strontium being big, it's the opposite. So let's see how we did. I got these visuals I wanted to show you, kind of showing that whole diagonal pattern. As you can see, we are slowly getting smaller left to right. Magnesium 737, strontium 549, phosphorus at over 1,000, antimony at 833. So again, a little variation here, but as you can see, these guys really want to defend because they're stable. You can see how high these numbers are. And then they are getting smaller as you go this way, 1,514. And again, there's little exceptions. That's okay. And then electronegativity-wise, so we hit that on the spot on the head. Because again, these are trying to gain electrons, and you can see that these values are a lot higher, especially fluorine's 4.0 compared to the